To first order, the moon is divided into two major provinces. Paul and the others have already commented on this. You have the lunar mare, which are the relatively young basaltic terrains that are relatively flat and have relatively few craters, and the older highlands, which are primary crust, north acidic. They're heavily cratered, and relative to the mare, they're rough. Okay. The surface of the moon is covered by a fragmental layer which has been called the regolith, and it's basically loose, incoherent rock material of a variety of sizes and compositions, all churned up. Covers the entire moon, and it ranges in thickness from a few meters on the mare to perhaps tens of meters on the highlands. And it forms particles that range in size from submicron all the way up to big boulders. There's essentially two processes going on: pulverization by bombardment, which is making things smaller, and at the very small scale, agglutinate formation, which is sort of taking small particles and putting them back together. The next slide. This is just to emphasize the heavily cratered nature of most of the moon, and that over billions of years there's been lots of time and lots of events to churn up the surface layer into the regolith that you will land on and operate on. Next slide. Key point here is the lunar surface is not JSC1, 1A, or whatever number you want. This little vial of material represents one version of a particular size fraction of the lunar regolith. So that's fine depending on what you want to do, but two important points. The surface has all kinds of materials in it that are not represented in these little vials, and there is no simulant that represents all of the physical variations of the lunar regolith and all the compositional, both chemistry and lithologic variations. So these different simulants that exist are good for particular processes that you want to test, but they're not a representative of the surface of the moon. Next slide. Okay, when you look at a lot of the data that's been published on the lunar regolith, it's important to bear in mind a couple of things. One is that we actually have a number of different kinds of samples, from scoop samples and drive tubes, and the rotary coring that was done on a couple of the missions. But all the analysis were done on a specific size fraction. Typically, they're all conducted on the less than 1 millimeter size fraction, and typically they're different kinds of analysis. Rock analysis and chemical analysis are done on different size fractions of a subset of the finer material. There are different size aliquots given to different people. Different labs did the analyses. Essentially, there's been no single sample for which everything, chemistry, mineralogy, and all kinds of other things have been done. It's all on different samples, and typically the material is heterogeneous enough that when you compare them, you're actually looking at different materials. So you got to sort of take a lot of the composition and information with a grain of salt and represent and recognize that there's a lot of variation that's not expressed in the analyses, and the individual samples are more complicated than a single analysis will indicate. Next one. Okay, the regolith, as I said, is produced by impact bombardment over billions of years, and it's broken up into something that looks like this, where you've got the surface regolith, which is the completely disaggregated, transported loose material with a range of particle sizes. At some deeper level, below some number of meters, extending down perhaps a few kilometers in the highlands, is stuff that's been broken up but is more or less in place. And eventually you get down into large blocks and into fractured crust, and then eventually at some huge number of kilometers, the stuff is intact and essentially unfractured. It's this near surface layer, the upper few meters, that you'll operate on and dig into. And as I said, there's variations in the thickness. This is the Apollo 15 landing site. This is Hadley Rill. When you look at the far wall here, you can see bedrock in place. These are lava flows and a couple of meters of regolith on top. That's the regolith that was developed in place over the last 3.5 billion years. This stuff is locally broken, but it's in place. This is where the lava flows came out and solidified. And there's layering in here. There has been suggestions that in places there might be older regolith layers interbedded with the lava flows, but that's not actually been observed yet. You can estimate the thickness of the regolith in different places by looking at the morphology of small impact craters, which is illustrated down here. When you have a nice simple bowl-shaped crater, it suggests you're still within the broken up regolith material. When you get into flat-floored craters, that tells you you're now excavating into the bedrock underneath. And so you can take these morphologic characteristics and map out the thickness of the regolith in an area. Next slide. There is layering. When you look at the Apollo cores, there's a variety of layers that were observed in them. In many cases, there's quite a few layers, 10, 40, 50 layers of different kind of units that are all relatively thin, a centimeter or so. This is one cross-section at the Apollo 16 site where people have tried to map from the drill cores and the self-recording penetrometer data some of the layering. What's clear is that there are layers locally, but they do not extend very far laterally. And it's because you've got an impact process that's layering material on top of each other from local nearby events, and occasionally a bigger event from more distal distances. So there is layering, and you can see it in the grain sizes here. There's all kinds of variations here suggesting there are all these little different layers. This is more of a lunar science issue than an operational issue, in the sense that this is to first order all the same stuff, and when you're digging in it, it's more or less the same sort of physical properties. Next slide. There's a certain amount of mixing that goes on that's a function of time and depth. This is a little cartoon that dates back from the Apollo era, where you look at the depth of turnover from fractions of a millimeter up to 10 millimeters, and the time it takes to excavate and mix to that layer. So you can see that in areas that are 4 billion years old, which is the highlands, you've excavated down many times, hundreds of times, down to depths of 10 meters. When you get down to younger ages, less than a billion years or so, you've only excavated down less than a meter, and you've only excavated it a few times. So there's a variety of mixing. The highlands regolith, which dates to the earliest history of the moon, is very well mixed to a very significant depth, whereas the mare are much less well mixed on a global scale. I mean, you do see pieces of highlands material mixed in with the mare regolith, and vice versa. You see pieces of the mare mixed into the highlands regolith. Next slide. Okay, I'm going to talk about the particles you're going to encounter on the surface. Next slide. Size frequency distributions have been done on all the returned material, and there's an infinite number of little graphs and charts that illustrate the statistics for different frequencies. It's important to remember that this is only the fine scale material that was analyzed. So all those rocks you see, for example, in this cartoon here, none of those are in the statistics. Okay, this just represents the less than few millimeter size fraction. Some definitions have been created over time. Soil was referred to as anything less than a millimeter in size. Occasionally centimeters been used. Coarse fines are the 1 to 10 and or the 4 to 10 millimeter size fraction, and the other term is dust. And when you go back and look at stuff in the Lunar source book, for example, it talks about dust as being the part. Okay, dust originally was defined as the less than 50 micron size fraction. Occasionally 20 microns was used. According to Dr. Mendel in the corner there, Constellation is going to use 10 microns. But you need to be careful when you look up information on dust, what size fraction it was done on. When you look at the fine fraction of the material, most of it, 95% or more of it, is less than 1.5 millimeters in size. So it's once you exclude the larger rocks, it's a very fine material. It's like flour. Dust, which is in this context the less than 50 micron fraction, makes up almost half of the material. So if you scoop up in between the rocks the fine material, half of that is going to be less than 50 microns. There are relationships with the particle size and the age of the particles. The more mature the regolith is, the finer the material is going to be compared to a relatively immature young regolith, because the process is continuous micrometeorite bombardment over time, making the rocks into little dust grains. Next one. There's also rocks on the surface, and these are the kind of things that are relevant to traversing the surface and landing and things. This is a relatively fresh crater on the Mare. This is a lunar orbiter picture from some time ago. Light's coming from the right here, and you can see the rocks and boulders scattered around the exterior of the crater. When you look at the surface in radar, you often see a picture that looks like this. Here's a crater rim and a bright area of ejecta around it. That's the roughness of the surface due to rocks and fragments in similar scale to the radar wavelength. So the moon's been mapped at 3.8, at 12, at 70 centimeters, and depending exactly on the geology, you see these effects around craters, which are telling you the distribution of particles at those size ranges around craters. But it's a good way to look for rough areas when you can't actually resolve them spatially with an image. This is a model of the the lifetime of rocks on the surface is function of how big they are, and this is sort of assumes a particular impact flux model over time, where depending on what model you assume, you'll get different lifetimes. But the bottom line is here that after some few tens or hundreds of millions of years, you will essentially destroy rocks. So the rocks that are exposed on the surface are all relatively young compared to the surface itself. So the mare, for example, are 3.5, 3.6, 3.4 billion years old. The rocks that are exposed here are much younger. They're on the order of tens of millions of years or hundreds of millions of years old. After that time, they go away. Next slide. The size-frequency distribution of the rocks has been mapped originally using the surveyor images and also with the Apollo surface images, and you get power law distributions that look something like this, where most of the material is relatively small. In this case, at the Surveyor 7 site, which was the roughest of the Surveyor sites, rocks bigger than 10 centimeters or so cover only about 10% of the surface, and they're randomly distributed around the surface. Greater than a millimeter only covers 18% of the surface, so they're relatively few. The caveat on the Surveyor data is that the counting areas are relatively small. Each site had about 6 or 7. Some of them range from a couple hundred square meters, but some of them are only a few tens of square centimeters. So the data were sort of put together, and then a line was drawn through it. And unfortunately, the original data is gone now, and so all we're left with at this point is somebody's idea of what the best fit to the original data were. And that's represented by these curves here for the Surveyor sites. Next slide. They also looked at the rock distribution on the Apollo missions. There are lots of surface images. They did a couple of things at each of the stations. They took a panorama set of pictures, and along the EVAs they collected a series of images, and Henry Moore and some other guys back in the Apollo era compiled the statistics for all this. And basically what they did was they looked out 10 meters and they made some maps, which I'll show you in a second. The important thing to remember is that if the rock wasn't within 10 meters, it didn't get incorporated into the statistics. And there's somewhat of a bias in the sense that they drove and stood in places that were easy to drive and stand in. And so if there was a huge rock over there on the other side of the room, it didn't get incorporated into the statistics because it wasn't nearby. But to first order, rocks in the scale of a few centimeters cover between 25 and 90% of the area. And what you observe is that when you're near a fresh crater, that's the area where you have most of the rock fragments. You get out into intercrater areas where there are no fresh craters, the distribution goes down considerably. And you can see the comparison between these two pictures. The top picture shows a fair number of fragments on the surface. This picture was taken on one of the rays at the Apollo 16 site from South Ray Crater. The lower picture shows an area in between the rays where the rocks are not as frequent. So the distribution of rocks on the surface is relatively well understood. In one sense it's random, but in another sense it's really associated largely with fresh craters. So if you're going to land on the surface of the moon or operate an area, if you stay away from the relatively fresh craters, you won't encounter rocks. And the fresh craters are easily recognized in images as well as by other kinds of thermal and radar data. And you can see that if you look at different size rocks that were calculated between 10 and 20 and 50 centimeters, the percent of the area that's covered by these rocks is all very small. It's less than a few percent bigger than 10 or 20 centimeters. So the large rocks are relatively rare. There are, the pathologic rocks that are, tens of meters in size, but those you'll see. From Lunar Orbiter, we'll have half-meter pixel images, and so the big multi-meter scale rocks will be easy to recognize, and you'll know where they are to stay away from them. It's the stuff in the smaller, which will be the sub-resolution images that you won't see in the Lunar Orbiter picture or in the LRO pictures that are going to be of concern, and you're going to have to use other ways to infer their presence. Next slide. These are two of the maps from the Apollo site, Apollo 16, Station 1. You can see a relatively low density of rocks here. 10 centimeter rocks cover less than 1% of the area here. So this was the near field where they didn't collect any data. This extends out about 10 meters. There were some shadows in places where they didn't get data, but you can see what the distribution of rocks is. Here at Station 11 on North Ray Crater, there's a considerable amount of rock frequency, and you can see how many more rocks there are there. But if you were going to land at a place, you wouldn't land here. You'd go someplace like this, Station 1, to land, and that's easily determined from the kind of images we'll have. So these kind of places can easily be avoided. Next slide. Okay, dust. This concerns a lot of people for a lot of different reasons. There are health effects possibly associated with the dust, and there are clearly mechanical effects associated with it. During the Apollo mission, when they got dust in the rings and in the helmet seals, they became very hard to reclose. The material is very rough because of the agglutinates that are in there. It's a glass, so it's very sharp and very rough, and it can be a problem, scratch some of the camera lenses and things, and so it's something you're going to have to deal with. Larry Taylor and his colleagues have been looking at the chemistry and size frequency distribution of the dust for a number of years, and this represents the analysis they've done on the less than 50 micron size fraction. And you can see when you exclude everything bigger than 50 microns and then do an analysis, there's a peak in the data at some few tens of millimeters, micrometers, excuse me. So there's a peak here, which is a function of the age of the material and how it was formed, but it's not a uniform distribution. So most of the material you're going to encounter in the dust fraction is going to be less than a micron in size, assuming that the stuff actually comes apart. There's a question about whether the van der Waals forces will keep it together in clumps, and the extent to which you can actually liberate 1 micron or 1/10 of micron particles individually to get loose. But when you dump it on a surface and then wipe it off, that very fine fraction will remain on that surface. So from a mechanical standpoint, it will be an issue. 95% of the less than 50 micron stuff is less than 2 microns, and you can see that there's some variations depending upon the sample that was analyzed. There are variations in the size frequency distribution and the composition. Next slide. The other issue that's come up about dust is the plume of material that was generated by the LEM descent. On all the missions, they observed some dust mobility at different altitudes. What appears to be the case is that Apollo 15, which came down almost vertically, generated the most obscuration phenomenon. The images there was a camera looking out of the LEM window, and there's a set of movies that have been floating around now, and people have looked at those. The caveat on the movies is that it was a very slow frame rate camera, and so as the stuff traverses across the frame, it essentially smears out across the frame, and so it looks much more opaque than it is. So you talk to people like Jack Schmidt, and you ask him, what did it look like? Did it look like the movie, or did it look less opaque? And his comments is that it's always less opaque, that because of the frame rate of the movies, it looks much more dense than it was. The material, though, is put into a ballistic trajectory, and it's blown across the surface, and then it lands. At the Apollo 12 site, here's the LEM. The vehicle came in from the right, traversed the surface, and finally set down here. And you can see there's a scour mark running across the surface where the engine plume impinged on the surface and blew the fine material away. And you can see some of the scour marks underneath the LEM on the Apollo 11 and Apollo 12 surfaces. So it's an issue. There is some obscuration. In a few cases, the surface was completely obscured on the last few, 10 meters or so. So it's an issue that you're going to have to deal with, but it's going to happen no matter where you are on the moon. Next slide. We'll talk a little bit about the physical properties. Most of the physical properties experiments, or data, if you will, an understanding that we have is sort of inferential. The only real direct physical properties experiments that were done on Apollo were the self-recording penetrometer and some of the trenching. And even the trenching was a little ad hoc because they really didn't have very good control on the depth and the geometry. A lot of analysis were done on the particles that were brought back, but in each case, all the cores were disturbed by the process of drilling, be it the drive tubes or the rotary coring. So there's a little bit of uncertainty associated with the physical properties that were derived from there. The Lunar experiment had a cone penetrometer on it as well, so there's lots of data from there, but that only sampled the upper few centimeters. So we have a pretty good understanding, but the details, I think, are still, there's a lot of uncertainties in the details. Next slide. When you look at the material, there's a whole range of particle sizes and shapes A lot of the material is angular because it's broken up rock fragments. It's agglutinates, which are pieces of individual particles that are re-glued together by melt associated with the impact process. And so there's a whole range of sizes. This is an agglutinate where you can see all kinds of different shapes, glasses, individual rock fragments. There's a variety of materials and sizes in the regolith. Next slide. We know from the observations that the uppermost couple centimeters are relatively low density, and you can see that in the sense when the boot prints on the surface extend in a few tenths of centimeters or a centimeter or so, and then there's a much denser layer. From the data that we have, there's basically a surface density that goes down maybe 30 centimeters of about 1.5 grams per centimeter cubed, and then it gets up into 1.8 or 1.7 at deeper depths. But these data were cobbled together from the cores and from the self-recording penetrometer, and so there's a lot of scatter in this, and it's not a nice simple sort of bimodal distribution like this curve would suggest. There's also a variation in the density depending on where you are. When you're on the inner crater areas, you get one set of densities. When you get onto the rims of fresh craters, particularly small ones, the density is very low. And depending on hillsides and stuff, there's a whole range of densities that will be encountered on the surface. Next slide. As I said, there was the self-recording cone penetrometer and the Lunar data to indicate how much resistance there is to penetrating the surface. And it's illustrated here about how much resistance was encountered as a function of depth. And you can see essentially that as you go deeper, you encounter more resistance. And that's because the density of the regolith increases and the packing increases, and those particles have trouble getting out of the way from each other, so that the penetration resistance goes up. This is a comparison of different terrains. These are Lunar data, but you can see the difference between the crater margins and the crater walls and the inner crater areas. And this is just a compilation of some of the data from some of the Apollo sites that were analyzed and compared to the Lunar data. The next slide. This shows it, I think, most clearly. This is Aldrin walking across the surface. There's a relatively small fresh crater over here on the left, and you can see the difference in how far his boots went in as he walked across the crater rim here, and then when he got away from it. The boot prints here are several centimeters deep because the material is relatively soft, so he sank in farther. When he got out here in what we call the inner crater area, the boot prints are much more shallow because the surface is firmer and it'll support more load. Same thing over here. There's some LRV tracks and some, this is on a hillside, some boot prints, and you can see that this material is relatively soft and was pushed out of the way fairly easily. Here again is walking through a soft area. The boot prints are relatively deep. When you get out over here, they're much shallower. Now some of this is a loading issue. How much load you're putting on is a function of the surface area. As you can see, the LRV tracks come across here from what's presumably a more firm area across this relatively soft area, and the LRV tracks don't go in much deeper. And that's because the loading on the LRV wheels was very, very low. Next slide. As I said, the self-recording penetrometer was one of the instruments that we had to actually understand the subsurface properties. It was essentially just a rod that you pushed into the surface, and the stress that was required to push it in was recorded. And this just illustrates one of those little curves for one of the Apollo 16 stations. The point being that you can see there's a lot of variation in the penetration resistance as a function of depth, and that's attributable to some of the layering that's observed in the individual areas. And it was correlated with some of the material from one of the cores here, but there's lots of small scale, tens of centimeter, few centimeter variations in the material properties as you go down through the regolith. Next slide. Cohesion. The lunar soil is very cohesive. Illustrates a trench, some trenching over here. You can see there's relatively nice firm material. This is a high resolution image of a boot print. You can see that the boot print is very nicely modeled in the regolith here. The stuff compacts, the surface stuff compacts very easily, and you get it's very cohesive. Next slide. Now, one of the things that was done was people modeled how steep an angle you could have and how tall a scarp or a pile you could have before it would collapse. And the theoretical analysis suggested that you could have, depending on what kind of factor of safety you wanted to have, but you could get slopes that were 80, 90 degrees high, steep, and that were several meters high, which would suggest something the size of this wall here, in theory, would be stable on the surface, dug into the regolith. But when they actually dug on, for example, on Apollo 14, there were some trenching experiments, and what was observed was that once they got down a few tens of centimeters, the walls collapsed. So either those trenches were dug in a less cohesive material, or this analysis is wrong. In any event, there's some complication in some of the cohesive material properties of the surface that we don't yet understand. It's important to bear in mind that there's lots of local scale variation. I mean, you can see from the boot prints in the LRV tracks that in an area the size of this room, you're going to have rocks, you're going to have craters of different sizes. Some of those craters are going to be fresh and soft. Some of them are going to be older and firmer. Some of the craters will be relatively deep because they're fresh and have a rim. Others will be much more degraded and just have a slight depression. Next slide. Okay, trafficability, we touched on this a little bit. The LRV was used on 3 of the Apollo missions and climbed up to slopes up to perhaps 20 degrees on Apollo 17. The estimate maximum ability to climb was about 23 degrees based on simulations they did on the Earth. And they got up to something close to that, and there was a sentiment that that's about, they reached the maximum ability to climb. Now that was for a particular loading and a particular wheel design, so if you were expecting to climb slopes that were steeper than that, it's simply a matter of designing the tires and the loading a little bit differently. But the LRV performed pretty well. It didn't have any problems. They did have one problem where it was, when they got off it, it didn't have enough, there was no mass anymore, and the thing started to slide down the hill a little bit, so they picked it up and put it in a crater to keep it from sliding down the hill. Next slide. This is just a table. I don't want to go through this in any detail, but you can see that there's a lot of the lunar properties have a range. There's some uncertainty associated with it. I think from an operational standpoint, from a design standpoint, and even from a digging in the regolith standpoint, we understand the material properties well enough that it won't be a problem to design systems, as long as you have some robustness in your design and you can deal with a variety of materials. But you're going to have to deal with a variety of kind of physical properties if you're going to operate over any kind of spatial scale. Next slide. I'm going to talk briefly about the chemistry and mineralogy of the regolith materials. Next slide. As I said before, there's 2 basic terrains. There's a basaltic terrain associated with the mare and a more north acidic terrain associated with the highlands. And when you look at the different size fractions and different materials, there are chemical and lithologic variations as a function of size. As you go through the regolith and break it up into different size fractions, the chemistry and the mineralogy change. Next slide. This shows it. This is just the bulk chemistry, the point being that there is not much variation in things like silicon between the anorthosite and the basalt. There's only 5% variation in the amount of SiO2. There's a fair amount of variation in some of the things like titanium oxide. That varies from less than 1% to perhaps 10% in the high titanium basalts. There's some variation in the amount of aluminum from 10 to maybe 30% in the anorthosite. The amount of iron also varies significantly. Most of the iron is found on the mare. There's very little iron in the highlands, and magnesium and calcium kind of track in a similar way. But the bulk chemistry to first order is very well understood. Next slide. When you look at the composition of the material, these are all different samples and the colors are all different size fractions, you can see that there are variations, in this case, in the amount of iron in different samples and with different sizes. This is the amount of aluminum in the material. Each one of these color-coded bars are a different size fraction. And what you can see is that seems to be an increase in the amount of aluminum in the very finest fraction. In the case of iron, there seems to be less iron in the very finest fraction. Assuming you could actually, have a significant amount of material in this one isolated size fraction, you might have to deal with this. But you're going to encounter the bulk regolith in all these cases, which is what the red dot indicates. Next slide. You can also look, this is the same kind of plot. These are a whole bunch of different samples. This is just iron and titanium. Titanium's in blue, the iron's in red, for a bunch of different samples at a bunch of different sizes. And you can see there are variations in the chemistry as a function of grain size. This kind of information is most relevant to the people who are going to try to do ISRU, where you're interested in trying to get a particular element out of the regolith, and in that case, sorting the regolith by size may be a very beneficial process because some of it will have much more concentration in the material of interest than the bulk material will. Next slide. There's also a lithologic variation. The cartoons are kind of complicated, but basically the different colors illustrate different kinds of lithologic material in a variety of different samples. The sample numbers are illustrated here. This is modal abundance on the vertical axis, and you can see, depending upon the material, the highest composition, the highest fraction of material is the stuff in red, which are the agglutinates, which are these little fused pieces of material. Different mafics and highlands material and individual mineral grains all make up the other 50% of the material, and depending on whether you're in the highlands or the mare, the amount of basaltic material or the amount of a north acidic material will vary. Next slide. There's also a fair amount of variation across the surface. This is at a couple of the stations at the Apollo 16 site. The point, this was broken up into 4 different kinds of rock fragments, and you can see that as you go from station to station, the relative fraction of different materials varies across the surface. And this is because it's coming from different places and the impact process is mixing it. This is not a particularly relevant aspect to operations, but it does occur at the tens of percent level. Next. This again just illustrates in a graphic way the variation in the amount of material associated with different materials. In this case, these are 4 or 5 samples from the Apollo 16 site. You can see that the bulk of the material, the fine fraction, is agglutinates, then breccias, and the rest of the individual rock fragments and mineral fragments are relatively small. Most of the material is either agglutinate or pieces of breccia, because breccia is the most common sort of bulk rock in the highlands. Next slide. Same thing, this is as a function of size fraction, the kind of materials, individual mineral grains and rock fragments, and again you can see there's variation in different compositions at different size fractions. Next slide. And same thing, this is just looking at the agglutinate and glass and feldspar in a mare basalt sample from the Apollo 12, 15 and 17 missions, and you can see as a function of size there are variations in the composition of the material. Next slide. Okay, one of the areas that's of interest are lunar pyroclastics, mostly from a resource potential. Next slide. These were encountered at the Apollo 17 site, the so-called orange soil that was observed at Shorty Crater that Schmidt kicked up accidentally and caused a big sensation. These are little glass fragments that presumably were formed in lunar fire fountains where the lava was erupting, was tossed up into the atmosphere, well, not the atmosphere, but above the surface in something that may have looked like this. These commonly occur in Hawaiian basaltic eruptions where the stuff gets shot up above the surface. It congeals in the glass and falls back onto the surface, and it's exposed here in this orange soil. Next slide. They occur in quite a few places. Lisa Gaddis has looked at the spectral signature of the surface and identified quite a number of places scattered around. Most of them are associated with the mare. You can see all these little red triangles illustrate areas that presumably are pyroclastic deposits scattered around the planet. Perhaps the one that's drawn the most interest in terms of exploration and other discussions has been the Aristarchus Plateau. The reason they're or of importance to resources is because they tend to, because they're relatively simple particles, they saturate with solar winds, and so the solar wind content of the pyroclastic material is much higher than it is in some of the rock fragments. And looking at the solar wind, it gets implanted on the surface as a function of time, and smaller grains have higher concentration than larger ones. So the very fine pyroclastic material tends to have more solar wind absorbed on it. The other thing which also occurs in some of the glasses is ilmenite, or any of the iron oxides, is resistant to radiation damage, and so it has a tendency to retain solar wind particles. Most of the stuff is hydrogen. That's the stuff that's of interest, particularly in the polar areas, because it can be used to make water or fuel. And there are different amounts as the stuff ages, it goes from red to black, and the amount of solar wind volatiles that are absorbed also vary over time. Next slide. This just illustrates the amount of volatiles of hydrogen, carbon, nitrogen, and helium that are associated with the material. You can see that even in the Apollo samples, which were front side, low latitude samples, there's a fair amount of hydrogen associated with some of these samples. Next slide. Okay, next one. As the regolith sits on the surface over time, it matures, and primarily the issue associated with maturation is the formation of agglutinates. Over time, more and more agglutinates occur, and those are the things that are relevant to operations, because that's the hard, glassy little particles that tend to abrade everything. This just kind of shows as a function of more mature, going down this axis from blue to yellow here, the particle sizes become smaller, and the amount of agglutinates increase with time. There's also something called there's various ways to measure the maturity. One is using ferromagnetic resonance. Another way is simply with color, and you can map out the different amount of maturity of the regolith this way. But the important point is that more mature regolith has more agglutinates, it has more nanophase iron, it's finer grained, and it has higher amounts of solar wind implanted in it. Next slide. These are what some of the agglutinates look like. As I mentioned before, the agglutinates are little particles that are composed of smaller particles by the impact process. When you get a micrometeorite impact, you locally melt the surface material, and so you glue these particles together into little agglutinate particles, which are very unusually shaped. They're also typically very small, and they're very hard because of the glass. And they make up significant fractions of the volume of the regolith in lunar in mature soils, from a few percent at a minimum to, in some cases, up to 60%. So they're an issue you're going to have to deal with. Next slide. Again, this just shows that as the amount of agglutinates increase, the average grain size goes down. And this is what some of them look like. You can see in this large one on the top here, you can see all the individual little particles that are glued together. This is a cross section. You can see there's lots of voids in them with the larger particles held together by glass. Next slide. Iron is of interest to some people for resources and for other reasons, and a lot of it is associated with what's referred to as nanophase iron, where you make a small impact at micrometeorite scale and you vaporize the iron, which then precipitates, coats the grains, and so a lot of the lunar grains have a patina of very thin iron coating around the margins. And if you look at the next slide, this is a cross-section through one of those grains, and you can see there's an iron layer up here and then little blobs of nanophase iron in the interior. So this iron at very small scales coats most of the particles, and that's where a lot of the iron is tied up. Okay, go on. Next one, keep going. Impact craters. From an operation standpoint, the surface of the moon is completely covered with impact craters. At the scale that's relevant to landing and operations, less than a few meters, the lunar surface is saturated with impact craters, which means every time you make one, you destroy one, and so effectively the size frequency distribution doesn't change with time. If you're worried about impact craters greater than, say, 100 centimeters, a meter diameter crater, you're going to have about 10 of those in 100 square meters. You know, at the scale of the landers design that people are talking about, there's no way you're going to find an area where the footprint of the lander doesn't in fact have a crater in it. All the Apollo LEMs, all the surveyors, all of them were tilted after landing, and that was because they had one or more feet in a crater. So there's no way to get around the presence of craters on the lunar surface. It's just something you're going to have to deal with. Next slide. The craters have a range of preservations. Most of them are relatively old and somewhat degraded, but you can see in this picture of the lunar mare, there's some very fresh craters with ejecta and sharp rims, and there are more subtle depressions scattered around that are older craters. There's a continuous process. The fresh craters are the most concerned, because these are the ones that are going to have lots of rocks around them. These old degraded craters, the rocks are gone and the topography is largely gone, but there's still areas of soft material around them that have to be considered. Next slide. One more. Topography. When you look at the surface in images, there's a dramatic effect associated with the lighting. When you have high lighting, the surface looks relatively benign. As the lighting gets lower and lower, it looks much more dramatic. This is particularly true of the pictures people have looked at in the polar regions. This is a piece of the highlands on the bottom, and you can see in this picture it doesn't look too bad. When you get down here at a few degrees lighting, it looks really dramatic. Next slide. The other thing which people have observed in the radar images are these areas of radar bright. These are typically associated with rough areas where there are rocks. They may also be associated, particularly in areas of permanent shadow, with deposits of ice. That's still an unresolved question, and hopefully will get resolved by the analysis that will be conducted on LRO and Chandrian. Next slide. Just want to touch on this quickly. The slopes are a function of scale length. When you look at the highlands are much rougher at scales of many kilometers than the mare. The mare is a nice smooth surface with the occasional crater. So the highlands appear much rougher when you're out at length scales, of kilometers. When you get down to the very small scale at meters, tens of meters, they both have about the same amount of roughness, because the roughness is largely due to small impact craters, and as I said, once you get down into the scale of a few meters, the lunar surface is saturated with craters, which means there's the same number of craters at 1 or 2 or 3 meters on the mare as there are in the highlands. The one thing to keep in mind, though, is when you look at a particular wavelength slope scale, what you're calculating is the difference in elevation over that baseline. So, for example, if you're worrying about 200 meters, all the topography and relief that has a wavelength shorter than 200 meters you don't see. So it's the stuff down here where there are no data that are most relevant to landing and operating on the surface. Next slide. This picture's been around a lot, and people keep going, oh my God, we're going to land there. There's kilometers of relief, and there's slopes that range from 0 to 35 or 40 degrees in this. But it's important to keep in mind, this is 400 or 500 kilometers across. The area nominally that's been talked about for landing is on the rim of Shackleton down here. You can't see the outpost area in this picture at that scale. Next slide. But here it is in high blown up. This is the cartoon that Kent Houston put together that's been around for a while with the nominal outpost configuration. When you actually look at the details of the slope, this is a slope map underneath, what you see is right along the rim crest here, the slopes are in the range of a few degrees. That's the slope you see in the radar data for the lunar mare, which are essentially flat. Okay, when you get, there's no surface on the lunar surface that has an RMS slope in radar data less than a few degrees. So if you see something with 3 or 4 or 5 degrees, that's not an issue. Similarly, there's this ridge extending out here, which has lots of flat space along the ridge. There are variations. This data are also relatively low resolution. Once we get the data, the LOLA data as well as the imaging data from LRO, we'll have a much better understanding of exactly what's going on along the rim here, along this ridge, and any other place that somebody wants to land. Next slide. Okay, I'm done. Thank you. There's seismic records, but those are all macroscopic impacts. They're relatively rare. The micrometeorite flux is understood from modeling. There's a group at Marshall that's been working on the problem for a while. What else? There's some data from things like LDEF and the station. I forget, I don't know exactly what the frequency is, but you will get the occasional micrometeorite. Can you calculate that one time? No. Those are all macroscopic, if you will. They're large enough to create a visible flash on the Earth. There was, when they brought the surveyor parts back on Apollo 12, they looked at some of the material, but they brought back the camera and a couple of struts, and there were some pits on there, but Dave McKay, I guess, did a lot of that work, and there were a few things that looked like true micrometeorite pits, but it was somewhat equivocal, and there were shadowing things depending on where the material was on the surveyor, so it wasn't that great an experiment. They've also, Fred Hertz and those guys have looked at the number of pits on an individual rock at micrometeorite scales and calculated what the frequency of those are. So there's data, but I just don't remember what it is. The data for the levitated dust comes from a couple places. One is there are a series of pictures that were taken by surveyor of the sunset horizon after sunset, and there was this glow observed that was interpreted to be a layer of dust about 1 meter thick, submicron particles that were forward scattering the light. The problem with that conclusion is that those observations occurred up to 2.5 hours after sunset. 2.5 hours after sunset, you have to be 300 meters above the surface to be in the sunlight forward scattering the light. So a layer 1 meter high is not illuminated by the sun at that point. So there's some problem with those things. The other data set were these sketches that were made from orbit, where they saw these streamers coming out from behind the terminator, and those were suggested to be dust at hundreds of kilometers altitude. Whether that really was levitated dust or zodiacal light is another argument that you can have. There also was, on Apollo 17, I think, there was the LEAM experiment, where they observed this increase in particle flux at the sunrise and sunset terminators that extended actually about 20 degrees. It was observed for a considerable amount of time. So if there's a layer, it's pretty wide. That was interpreted as stuff levitated by this charge differential coming across the surface. That's somebody's interpretation of those data. So there's some equivocal data that suggests this occurs. The real question is the amount of material that's actually being levitated. And the observations are that the retroreflectors have operated continuously with no apparent degradation. The lunar surface, the rocks on the lunar surface, are not coated with dust, and they've been there for hundreds of millions to billions of years. And the ALSEP, while it was operating, didn't see any significant change in its thermal state, which it would have if it was being continuously coated with dust. So it's not clear. I mean, clearly you can go in the lab and you can take very fine particles, expose them to UV light, and charge them, and if you put them in an electric field, they'll float up. That's just physics. Whether it's an operational issue, I think, is still an open question. So people have talked about experiments to do, and they range from very complicated electrical experiments, put stuff in orbit and all this other stuff, to just putting out a witness plate and seeing what gets deposited on it over some period of time. They brought pieces of the surveyor back. The surveyor was completely coated with dust, but it's not clear how much of that was due to the surveyor landing because the engines didn't shut off, so it was sitting there blowing dust up on itself. The Apollo 12 spewed stuff all over it, and what was just naturally deposited on it. So, yeah, there are analog samples. Those are fairly coarse. You'd have to get something that was very fine-grained and that was dry. I mean, the problem is that anything that's been in the Earth's atmosphere is got water adsorbed on it, so you got to get all that off before you're going to get the same electrostatic effects you're going to get on the moon. Offhand, there's a guy, Haranye at Colorado, I can give his contact information. He's done a lot of experiments on fine-grained material and how it reacts in electric fields. There's also Tim Stubbs at Goddard and a few other people who have been doing experiments on levitating dust. But those experiments are all from an electrical point of view. They're not physical, mechanical analogs. I don't know that there's a dust analog. They were making a number of different simulants at Marshall. They were working with the guys from the USGS to create a range of lithologies. Now, if they're working on they may be doing a pure dust one too. If they are, I didn't know that. Question in my mind is, if you've got bulk regolith, how much dust can you actually liberate from it? I mean, you've got this range of particles, but it's all mixed together. So maybe you can electrostatically levitate the fine-grained stuff right at the surface, but you're not going to levitate out from 3 centimeters depth that other particle. So there may be a finite amount of material that you can actually levitate, even if you have the appropriate charge phenomenon, just because it doesn't have enough force to push everything else out of the way and somehow extract magically all of the 1 micron or half a micron size particles. Plus you've got to overcome the particle-to-particle bonding. Yes, at the scale you're worried about for landing, the surface is saturated, which means that no matter where you go, the size-frequency distribution is going to be more or less the same. There are size-frequency distributions that will tell you for a given area how many craters of a particular size you can expect. The specific question you asked, whether the slope information is there, I think the answer would be no, but that would be relatively easy to calculate. I mean, you'd have to assume some range of how many fresh, intermediate, and degraded craters, and for a particular, for a 1 meter crater, if it's fresh, it's going to be bowl-shaped. With time, it shallows, the rim goes away, and so it would have lower slopes. That somebody could calculate that, but to my knowledge, that has not yet been calculated.